Real numbers. Part 4. Okay, our next section, the fourth section and the last section in this chapter, revisiting rational number and their decimal expansion. Okay, at first we have studied three sections, that is, first section is about Euclid's algorithm and Euclid division lemma, and the second section is about what is the second section? Fundamental theorem of arithmetic. Then the third section is on irrational numbers and their properties and some theorems related to that irrational numbers. We are moving on to the fourth section, that is revisiting rational numbers and their decimal expansion. So we are studying about the rational number family of real numbers again. Okay, rational family of real numbers again here. So here this is some quite interesting facts on rational numbers are studying here. Let us have a look on first fact. Theorem. Let x be a rational number whose decimal expansion terminates. Then we can express x in the form of p by q, where p and q are coprime and the prime factorization of q is of the form q raised to n into 5 raised to m, where n, m are non-negative integers. Okay, that is, by the theorem, what we can say that x is a rational number, okay, and whose decimal expansion terminates. That is, it have a decimal expansion which is terminating. That is what is, for example, 1 by 2. Its decimal expansion is 0.5. Then what about one more thing, 1 by 10, which is 0.1. Okay, if the decimal expansion terminates, then what we can say, x can be expressed in the form of p by q, that is x equal to p by q, where p and q are coprime. This is usual, that is, every rational number can be expressed in the form p by q, where p and q are coprime. But what is the importance here? The prime factorization of q is of the form q raised to n into 5 raised to n. That is, for the prime factorization of q, only two digits are present. That is, only two prime numbers are present in the prime factorization or the decomposition of q. That is 2 raised to n and 5 raised to n. That is, 2's and 5's are only prime factors which is present in the prime factorization of q. Okay, where n and m are non-negative integers. This is our theorem is about. Let us have a look on some examples. Example, at first we are studying about a 5. 5 is a rational number. Okay, since 5 can be represented in the form 5 by 1. Okay, its decimal expansion is terminating by 5 by 1 equal to 5. Then what we can say about that? By the theorem, we can express 5 as p by q, 5 by 1, HCF for p comma q equal to 1. Okay, then what about the decimal expansion of q? Q equal to 2 raised to 5 into 5 raised to 0. Since q equal to 1, we can represent q as 2 raised to 0 into 5 raised to 0. Okay, since since q equal to 1, we can represent it as in the form 2 raised to 0 into 5 raised to 0. That is, what is the condition here? N and m are non-negative integers. So, we can express q in the form of 2 raised to n into 5 raised to m, but m and n are non-negative integers. That is, n and m are non-negative. It can be 0. Since it is non-negative, it can be 0 also. Okay. So, here q equal to 2 raised to 0 into 5 raised to 0. Then, what about next? 3 by 8. What is 3 by 8? 0.375. So, what we can represent it as in the form p by q, that is 0.375 equal to 3 by 8. Then what about the decimal expansion of q? 8 equal to 2 into 2 into 2, that is 2 cube, which is also in the form 2 raised 2 cube into 5 raised to 0. Okay, 2 cube into 5 raised to 0. Here also the condition is satisfied. Moving on to next. Zero point zero eight seven five. How can we represent 0.0875 in the form of P by Q? That we are going to see now. That is, what is our theorem? If x has a decimal expansion which terminates, x is a rational number whose decimal expansion terminates, then we can express x in the form of P by Q. This is our first part of theorem. Okay. If decimal expansion is terminating, so we have to represent in the form P by Q. For representing that, we have studied earlier what to do. That is, we have to count the numbers after the decimal point, that is 1, 2, 3, 4. Then we have to multiply with the factors of 10. Here we have 4 numbers after decimal point. Then we have to multiply by 10,000. Okay, we are multiplying it by the 10,000 here. If we have 2 numbers, we have to multiply it by 100 and divide it by 100. Similarly, we are doing like this. Then what is this? 875 by 10,000. Okay, but what we need to express it in the form P and Q are co-prime. That is, the common factor between P and Q equal to 1. So let us check whether we can express it or not. Okay, it is 875 by 1000. So what we are going to do, we are splitting 875, which is 7 into 5 cube. What is 10,000? 10 raised to 4, and we are splitting it into 2 raised to 4 into 5 raised to 4. Okay. So here we have 5 cube here we have 5 raised to 4 here. Then by cancelling we will get 5 here. 2 raised to 4 is present. That is, here we have 5 cube, here we have 5 raised to 4. We will get 5 by cancelling each other. Then what is this? 7 by 80. Okay. 7 and 80 has no common factor other than 1. So that condition is satisfied. That is, HCF of P, Q equal to 1. Then what next? The prime factorization of Q is of the form 2 raised to n into 5 raised to n. What is the prime factorization of 80? That is 2 raised to 4 into 5. Okay. So this condition is also satisfied here. Hence we can say that theorem is right here. Okay. Then what about next? 13.333. Okay, what is that 13.333? In order to represent it in the decimal form P by Q, in the form P by Q, what we are going to do, here we have 2 numbers after decimal point, we are multiplying it by 100, dividing it by 100, but we will get 13333 by 100. Is there any common factor between 133, that is 1333 and 100? No. 100 have only factors 2 and 5. 1333 has no factors like 2 and 5. So HCF of these two numbers are 1. So that condition is satisfied. Then what is the decimal expansion of 100? 20 into 5, that is 5 square into 2 square. Okay. So what we can conclude? HCF of 1333, 100 equal to 1 and 100 equal to 5 square into 2 square. So by the theorem we can write this like that. Then, so we are saying this number is a rational, this number is a rational. How these numbers are came to be a rational number? Let us check. You have to know that is, with this previous knowledge, rational number has either the terminating decimal expansion or non-terminating recurring decimal expansion. Okay. So, in order to distinguish between a rational number and irrational number, what we have to check? Whether it has a terminating decimal expansion. If a decimal expansion is terminating, then that is a rational number. Or another thing, if it has non-terminating but recurring decimal expansion, that is non-terminating but repeating. Repeating means we can say what is next. Okay, that is 0.333, 0.272727. 0.565656, that is non-terminating, recurring, that is repeating decimal expansion, then that numbers are came into the category of rational number. Okay. So to check if it is a rational number or not, there are two chances, that is there are two ways. Either it has a decimal terminating decimal expansion like this, or another case it has a non-terminating but recurring decimal expansion. You have to keep this in mind. Okay. Let us move on to our next theorem. Let x equal to p by q be a rational number such that prime factorization of q is of the form q raised to n into 5 raised to m, where n and m are non-negative integers, then x has an expansion which terminates p and q are co-primes. Okay. So what is here is something converse of our previous theorem. That means converse means something ulta. That means in previous theorem we have studied if x has a decimal expansion which terminates, then we can represent x in the form of p by q, where p and q are co-primes and the prime factorization of q has only factors 2 raised to n into 5 raised to n. Here we are studying something reverse of that, that is if x equal to p by q be a rational number such that p and q are co-primes and the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n, m are non-negative integers, then x has a decimal expansion which terminates. That is reverse of previous theorem. If x is of the form p by q and q has only prime factors 2 and 5, then its decimal expansion will automatically terminate. Okay, something reverse of previous theorem. Let us have a look on its example. Since we know that 6 has a terminating decimal expansion, so we can establish the theorem that is 6 equal to 6 by 1, that is equal 6 comma 1 equal to 1 and 1 equal to 2 raised to 0 into 5 raised to 0, that is q equal to 2 raised to 0 into 5 raised to 0. Why? Since n and m are non-negative integers, n and m can be zeros. So here we have q with the decimal, prime factors 2 and 5 only, 2 raised to 0 and 5 raised to 0 only. Then also it is of the form p by q, p and q are co-primes. So what we can say, automatically decimal expansion will terminate. It is terminated because 6 by 1 is 6. Decimal expansion of given number is 6 itself. Okay. Then about next question, 5 by 8. So here 5 by 8 is of the form p by q, then p and q are co-primes, that is HCF of them is 1, then q equal to 2 cube into 5 raised to 0, okay, that is q equal to 2 cube into 5 raised to 0, that is q has only prime factors 2 raised to n and 5 raised to m, that is 5 raised to 0 and 2 cube here. So by the theorem the decimal expansion will terminate. Let us have a look whether it terminates or not. That is, at first we are changing 8 in the form 2 cube into 5 raised to 0 or 2 cube. Okay. In order to get the decimal expansion of this, what we are going to do is multiplying 5 cube and dividing 5 cube. Why are we doing this is in order to get some multiple of 10 in the denominator, or making the denominator as a multiple of 10 only. We are multiplying each term by 5 cube, that is numerator by 5 cube, denominator by 5 cube. Why we have to do this? We want to get some tens multiple in the denominator. So here we are multiplying 5 cube because we have here 2 cube. Okay. So in order to get 10 cube, we are multiplying here the 5 cube. Then 625, that is 5 raised to 4, 625 and divided by 10 cube, which is equal to 0.625. Okay, so it has a terminating decimal expansion. Then what about next? 6 by 80. Here 80 equal to 2 raised to 4 into 5. So whether HCF of these two numbers are 1? No. It is 2. But whether we can have this theorem, we are going to simplify these two numbers. Since 2 is a common factor, on simplifying we will get 3 by 40. Okay, 3 and 40 has a common factor 1. And that is, they 3 and 40 are co-primes and 40 equal to 8 into 5. Okay, that is 2 cube into 5. Okay, so our conditions are satisfied. That is, it is of the form P by Q. P and Q have only common factor 1. And what is next? That and this denominator is of the form 2 cube into 5. So its decimal expansion terminates. Okay. So in order to find what is its decimal expansion, let us find out. So we are making it 3 by 40 here. 40 equal to 2 cube into 5. Now to get 10 in the denominator, we have to multiply a 5 cube here. Okay, here we have 2 cube, we need a 5 cube. So we are multiplying each term by 5 square in order to get 5 cube. So what we will get? 3 into 25 by 10 cube. So 3 into 25, 75, 75 by 1000, 0.075. Okay, so it has a terminating decimal expansion. Then what is next? Another theorem. Let x equal to p by q, where p and q are co-primes, be a rational number such that the prime factorization of q is not of the form 2 raised to n into 5 raised to m, where n, n are non-negative integers. Then x has a decimal expansion which is not terminating. Okay, so what is the theorem? Not terminating, repeating, that is recurring. So what is the theorem is about? If x equal to some p by q, x equal to an integer by another integer where p and q are co-primes, that is common factor among them is 1, then if q has any other prime factors than 2 and 5, that is if q possesses any other prime factors than 2 and 5, then what we can say through this theorem? That is, x has a decimal expansion which is non-terminating but recurring. Why it is recurring or repeating? Since it is a rational number. Okay. So any change in the decimal expansion of 2 raised to n into 5 raised to m, that is, if we have some 3 as a prime factor of q, then it has a non-terminating recurring decimal expansion if it is a rational number. Okay. Then let us have a look. 1 by 3. It has a prime factor 3 in its denominator. So what is its decimal expansion? 0.3333. That is non-terminating. Then what about next? 3 by 11. What is its decimal expansion? 0.272727, etc. Why it is so? Since q has a prime factorization other than 2 raised to n and 5 raised to n. Okay. So how we get 0.272727? Let us have a check on that. That is, we have to divide 3 by 11. So we are taking 3 as our numerator here and 11, sorry, numerator no. The numerator as our dividend here and the denominator as our divisor. Okay. Since 11 is not completely divisible on 3, we are putting a 0 as usual. So what we will get? 30. 11 into 2, 22. Okay, it's fine here. So for putting 2, we are putting a point. Since we are adding a 0, we have to put a point here. So what is this point? 2. 11 into 2, 22. Then what is our remainder? 8. Okay, since 8 is not divisible, since to continue division, we are putting a 0 here. 18. 11 is 7 times in 80, that is 11 into 7 is 77. Again we got a 30 here. Okay, again on doing we will get 80. Again continuing, we will get again 30. That is, it will continue like this, 0.272727, etc. Why it is so? It has a denominator which has a decimal expansion which is different from 2 raised to n and 5 raised to n.